Hello everybody and welcome to our GIS lab and hydrologic analysis with special attention to watersheds and surface flow patterns. These hydrologic functions are pretty cool and they let you use GIS to analyze the shape of the landscape in some sophisticated and interesting ways. Now the methods we'll discuss here only apply to surface hydrology though. Groundwater movement's a whole different animal and requires knowledge of spatial distribution of aquifers, which we don't have, so we're going to stick to the surface stuff in this lab. Surface stuff can be pretty fun though, like we're going to generate the watershed that drains into Picture Canyon. We're also going to do some stuff with flow accumulation, which basically tells us the catchment size for every cell on the landscape. The flow accumulation raster is then useful for finding stream paths, and it's also for finding areas where flow concentrates, and that might therefore be susceptible to flash flooding. It is also used for generating a general index of topographic wetness, which can be useful for a habitat analysis. And finally, we're going to apply some tools we've used before to calculate slope and aspect statistics within the watershed. Now all of this magic starts with flow direction. We need to know exactly which direction water flows over every point on the landscape. Now there's a few methods for doing this, and in this lab we're going to use a method called D8. It stands for 8 direction, and basically it's just a way to steer the water into the single neighboring cell with the steepest slope. It's the simplest method and one that produces data that can be used as inputs for other ArcGIS hydrologic tools. So it's a good one. It's the one we're going to use. But I'll just briefly explain what the other two methods are. They're interesting and they provide generally more precise hydrologic statistics. They're more sophisticated. Unfortunately, they don't all produce data in a format that all the other tools can use as inputs, and so they're less useful for several other purposes. Now the first method, called MFD for multiple flow direction, it actually sends water into every downslope cell. So in this example, we see 4 neighboring cells that are downslope from the central cell, and so this method will actually steer water into all 4 of those. The one with the steepest slope will get the greatest proportion of flow. This other method, called DINF, stands for infinite direction. Infinite in this case just means that it can be any value between the range of 0 and 360 degrees. So it doesn't mean that there's an infinite number of directions. It'll steer it into, well, it's basically like aspect. It steers it into the steepest downslope direction. So in this case, the aspect at that central cell is 158 degrees, and so this method would send water flow in exactly that direction. It's not exactly the same as aspect. They use a slightly different algorithm, so you come up with slightly different numbers. But also, they calculate direction in a mathematical direction instead of compass direction. So remember that in compass directions, 0 degrees means due north, and values increase when you go clockwise. But in mathematical directions, 0 degrees means due east, and values increase counterclockwise. For those of you who don't remember polar coordinates from trigonometry class in high school, let me quickly show you the difference between that and compass direction. In forestry and in most ecological and land management fields, we consider north to be at 0 degrees on the compass, and values increase in a clockwise direction. So east is at 90 degrees and south is at 180 degrees. And whenever you calculate or measure aspect, then those aspect values are recorded using this system. Mathematical fields, on the other hand, people more commonly calculate direction in the form of polar coordinates, where east is at 0 degrees and values increase going counterclockwise. In this system, north is at 90 degrees and west is at 180 degrees. And actually, direction is generally reported in radians, where 180 degrees is equal to pi radians, or roughly 3.1415 radians. It's easy enough to convert from radians to degrees, though. Now the folks who wrote this DINF function apparently used the mathematical strategy. So the DINF values are reported in degrees counterclockwise from east. And in this example, an aspect value of 158 degrees is equivalent to a DINF value of 292 degrees. They both mean the same direction though. Anyway, we'll be using the D8 method to calculate flow direction because it's most versatile for later on hydrologic analysis. It's simple and gets the job done. So let's take a closer look at this D8 method of determining flow direction. So we start with our DEM. We see all the elevation values scattered across all these cells. Suppose we want to figure out the slope direction from this particular cell here. So the D8 method is going to flow into one of the 8 neighboring cells. And the question is, which of those 8 neighboring cells has the steepest downhill slope to it? So the algorithm calculates the percent slope in each of those 8 directions, identifies which of those cells has the steepest downhill slope, and then directs the flow direction exactly and straight into that particular cell. Then it does this for all the cells on the landscape, so we come up with a raster of flow direction values. And then we use this full raster of flow direction values to calculate all of our surface hydrologic functions, including the watershed that drains into Picture Canyon. And now that we have this cool flow direction raster, we can use it for a number of hydrologic functions, including finding out where water would flow from any point on the landscape. We can also easily calculate the entire catchment that drains into any particular point on the landscape. And we use these same methods to calculate the entire catchment area that drains into Picture Canyon. The process works incrementally, one cell at a time, and before you know it, you have the whole watershed. Now all this is fine as far as it goes, but the success of all these surface hydrologic functions make an important assumption about the underlying flow direction raster. Basically, they all assume that there is some outward flowing direction from each cell. Some neighboring cell has to be either lower in elevation or at least equal in elevation in order for water to flow in that direction. But if all neighboring cells are higher than any particular cell, then there is no outflow direction. In these cases, surface hydrological functions simply stop. Regions like these are called sinks on the landscape. So what do these sinks mean to you? Primarily, your flow direction raster will no longer allow for continuous movement across the landscape. Flow direction raster will try to send water into the lowest neighboring cell, but that neighbor just sends it right back. When flowing water reaches these sinks, it stops. This means that any analysis that uses this stream flow, such as defining watersheds or drainage routes, will also stop. So the solution is simply to fill these sinks. Unfortunately, there's an ArcGIS tool that's designed for exactly this. We go to Arc Toolbox, look in the Spatial Analyst tools, go down to Hydrology, and here we go. It's the Fill tool. Open it up. Here's where we give it our DEM that we need to be filled. We have to give it a new name. This is going to be the output raster that will have all these holes filled. Now the Z limit is it's a measure of how deep you're willing to fill. Sometimes you have genuine pits and valleys on your landscape that you don't want filled, and so here you can set a threshold. If the pit is greater than, say, 20 meters, then you're going to just leave it as a true depression on the landscape. We run this fill tool on our DEM and it finds all those sinks and simply increases the cell values until there is hydrologic flow through them. So now when we run the flow direction tool, we get a raster that really does allow continuous movement through the landscape. Now, just to be clear, the fact that you have sinks to be filled doesn't mean your original DEM was wrong. The actual landscape has plenty of real low spots and drainages that don't stop the true flow of water. When a real stream encounters a low spot, it just fills the pool until the water is high enough to drain out the other side, and then it continues flowing downstream. The reason we had to fill the sinks for this hydrologic analysis is that these hydrologic tools just aren't near as sophisticated as the real world. They treat flow direction cells as if they were one-way streets, and you just can't go the wrong way on a one-way street. We only use the fill DEM to produce a working flow direction raster. Then when we go back to other surface or topographic analyses like slopes or aspects, then you're really better off using your original DEM. Okay, I think that's enough for a brief introduction into the topic. Let's go ahead and start in on those labs. You're going to do several cool things in this lab. Clearly you're going to create a watershed like we've been looking at based on that flow direction raster. We're also going to do a flow accumulation analysis, which would help us identify where streams are on the landscape, and this will also be a basis for a TWI, topographic wetness index. We'll do some of the basic surface analysis that we've done before, calculating slope and aspect across the landscape. We'll also calculate the area within this Picture Canyon watershed that lie within certain slope ranges and lie north facing and south facing or just flat. And finally we'll take a quick look at TWI, the topographic wetness index, and I think it's a good lab. I think you'll enjoy it. Talk to you soon.